my talk has this mysterious title, The Power of Large N. I apologize to those who already have heard parts of this talk, but so I'll start just a bit introductory with different large N limits. And of course, the focus of my talk will be the new large N limit that's available in tensor models. But let me just remind you about more basic large N limits. For example, the oldest one is what you would call the vector large N limit, where the fields are just transformed as vectors under ON. And for example, you have the famous Wilson-Fisher linear sigma model, basically the 5-4 theory with ON symmetry. And these type of theories are solvable in any dimension, basically in any incarnation. And we always take the large N limit whilst keeping the G, this coupling constant G times N fixed. And the reason these theories are always solvable is because they're dominated by a very simple set of diagrams, the set of bubble graphs. And now in the context of ADS-CFT, these theories are dual to theories where the dual theory has some massless higher spin fields. I won't talk too much about this, but that's also a quite generic feature. Now, at Hopf limit and planar graphs, that's probably the most famous one. And by sheer coincidence, it's great to have Gerhard Hopf here in the front row. So the reason this limit is so important is because of QCD, right? So the generalization of QCD from SU3 to SUN has been an amazing tool for many years. And the basic breakthrough from, I believe, 1974 was that the perturbative expansion is dominated by planar graphs. So the basic counting rule, so for example, if you have Yang-Mills coupling G, and you look at the correction to propagator, it's very convenient to use the double line notation where each, say, gluon line is represented by a quark and an anti-quark, two arrows in the opposite direction. And then each loop is just an index loop which contributes a power of n. So you essentially have the correction to the free propagator will have 2 powers of g and 1 power of n due to the index loop. So it's clear that one has to keep g squared times n fixed to obtain sensible results. And so this has had a variety of applications, and one of them is, of course, to ADS-CFT. So now, this year, we're celebrating 20 years of ADS-CFT, and I think it's safe to say that if not for the large N limit, we probably would have discovered it much later. Because so far, I mean, the essential trick is to think about large N gauge theory, which can be thought of as living on a stack of many coincident branes, which create a classical field around them. So the large N limit is a kind of semi-classical limit, which was exhibited very nicely from the D-brane picture. So you all know this. I don't have to dwell on this. But I think it's safe to say that so far, most of the results are in the leading planar limit. Like people have discovered, for example, the integrability of the leading planar limit of the theory. And the tests, the effects of quantum gravity are really buried in the 1 over n squared corrections. And maybe in the next 20 years, we will learn more about these effects. So far, there is rather limited information about them. So large N limit came in absolutely crucial in these 20 years of ADS-CFT. Now, one thing that's, I think, both unfortunate and fortunate is that the theory is still very complicated. The matrix large N limit is, is rather complicated because, in general, it's very hard to solve to sum over planar graphs. So one you need some kind of special trick, some extra symmetry. So one trick is what happens in ADS-CFT. A much older trick is what happens in very low-dimensional models, like matrix models. So for example, soon after 't Hooft's famous paper, there was work by Brzezinski, Parisi, and Zuber, who solved the one matrix model and also the quantum mechanics of one matrix. And there you can basically sum over planar graphs rather explicitly, and you can also enhance the 1 over n squared corrections in the so-called double scaling limit. So one really nice thing about the matrix quantum mechanics is that it just reduces to a theory of free fermions moving in this potential. And this is certainly an exactly solvable theory from which we learned a bunch of interesting results. This is my old review, for example, where some of it is described, but things keep happening in this direction. One thing that doesn't seem to have yet happened is a complete understanding of two-dimensional black holes. Like, essentially, the reason this model has been so fruitful is it provides a kind of toy model for a kind of holographic duality. Because if you think about the Feynman graphs, these planar Feynman graphs, they're dual graphs. So the Feynman graphs are just cubic, and their dual graphs are triangulated surfaces. And one can tune the coupling constant to the regime where everything is dominated by large graphs. From the point of view of the fermions, this corresponds to the Fermi level reaching the local maximum of the potential. Then there is considerable evidence that this is equivalent to string theory. Basically, this is quantum geometry, and you can replace it just by continuous quantum geometry, which is the quantum Liouville field theory. Basically, the 2D metric can be reduced just to the conformal factor, and you get this kind of connection to string theory. So in this particular case, we call this the non-critical two-dimensional string theory because there is one obvious coordinate x, and then the other emergent coordinate, which is this Liouville coordinate. So, but the understanding, so for a while, we've been trying to understand black holes in two-dimensional string theory. Well, not so much me, but many people. But I think the understanding is still rather incomplete. And there is no, basically, smoking gun for the description of two-dimensional black hole and non-critical string theory. There were some nice papers, for example, by Kazakov, Kutasov, and Kostov. But I think this problem still continues to interest people. And what I'll talk about is, in some ways, it's similar in spirit to this, but I think it's a richer system. It's also a quantum mechanical system, a large N quantum mechanical system, and also fermions show up, but in a very different way. But before I do that, let me just make a small digression. There are variants of this theory. For example, if instead of Hermitian matrix, you take a general real matrix, then there is going to be ON cross ON symmetry, which acts on the two different indices of this matrix. And then the interaction must be at least quartic. Now, the cubic interaction that I had for the Hermitian matrix is not allowed. And you can represent, so the surfaces now are not orientable in general. So there will be both the 1 over n squared corrections and also 1 over n corrections, which are typical for unorientable surfaces. But the main thing is that the propagators are now represented by two distinct lines, which can be represented by different colors. So, for example, red and green, and the vertex couples them together in this fashion. So again, in the large N limit, we find planar Feynman graphs. But when you actually see what the graphs look like, there is some restriction on combinatorics, because there will be alternating green and red loops. So the dual lattice made of, basically, you can think of, they look squashed, but you can think of them as squares. They have 4 sides. And the vertices of the square are inequivalent. There is a green vertex, red vertex, green, red. And they can be glued only in an orientation where red and red is glued together and green is glued together. In this case, it turns out it doesn't affect the planar limit too much. It's basically, again, given by the same theory. But it becomes important when you move on to higher rank tensors, which I'll describe in a second. So let me make a big leap from basically bifundamental representations of On cross On to the trifundamental representations of On cube. You take a 3 tensor, which is general 3 tensor, namely the 3 indices are totally distinguishable. So the propagator is going to have this index structure. And now the propagator line can be represented in a similar way to Hopf double line notation. Here you'll have triple line notation, and each line has a distinct color. So now you can write down several types of quartic interactions for this theory. It's no longer as unique as what we had in the case of, I should say that even here, it's not unique. There is also a double trace interaction. One can write another interaction, which is trace MM transpose times trace MM transpose. And these effects have been studied in great detail. The double trace interactions can be tuned to some special values, but in quantum mechanical setting, you can just forget about them. They don't get induced unless you force them there. Here, there is a similar story. There are, say, double sum interactions where you can just have phi ABC all squared. Then there are some more complicated things. But I would like to focus on this type of interaction, which is called a tetrahedral interaction, which is rather non-planar. If you draw the lines, okay. Yeah, if you draw the lines, there are 3 lines coming in, and the middle lines cross under each other. And when you think about it, you can see that this is actually a view of tetrahedron from one of the directions. There are some additional interactions. So the characteristic feature is that every 2 phi fields have only one index contraction in common. And with this type of chosen interaction, you can show that there is a new type of large N limit, which is exactly solvable. Yes? Is there a reason why it's ON and you didn't do UN? Does it have to be ON? No, there are variants where you have, for example, I'll mention later, you can have 2 SUNs and 1 ON. For example, if you have 3 UNs, it's so restrictive that it doesn't allow this tetrahedral interaction. But for the complex tensor, you can have SUN cross ON cross SUN, for example. So I'm just talking about what seems like the simplest thing that comes to mind. And then you can sort of start experimenting with this type of theory. And the idea is very similar to what we saw in the matrix model. You just start drawing graphs and count the maximal number of index loops that you can, colored index loops that you can have. So for example, you start drawing the vacuum graphs. This is like the simplest vacuum graph where you have 2, 5, 4 vertices connected together. And when you start sketching these index loops, you realize that with this non-planar tetrahedral interaction, you can get as many as 6 index loops, 2 red, 2 green, and 2 blue. And they pass under each other in this rather intricate way. So the leading propagator graph is, of course, n cubed, right? Because there are just n cubed degrees of freedom. And this gives n cubed times g squared n cubed. So you get the idea that you have to keep g squared n cubed fixed, which is rather different from a Hopf limit. and then you start sort of drawing more graphs, like for example these graphs, and then you again see that keeping this combination fixed, g n to the 3 halves, you again get something that scales like n cubed. And then it's possible to prove, which I'll exhibit quickly in a second, that nothing beats these graphs. And these have been called melon graphs. For example, this is like an insertion of a melon. This is 2 melons. I'll comment on this a bit later. So the original motivation for studying these so-called, so if you just draw this in 0 dimension, it's just a graph counting problem, similar to the one matrix model. And people initially hoped that this can help understand 3-dimensional quantum gravity, just like matrix models helped us understand 2D quantum gravity. And I think the original papers were around 91, 92 by these authors. I think the best of these papers actually had something like this tetrahedral interaction, but they didn't manage to, they tended to work with just a simple ON group and 3-index tensor. I think they had UN, and they didn't figure out how to analyze the large N limit. Then since 2009, there has been major progress due to first a paper by Gourau, then Gourau, Rivasson, and collaborators. And they actually coined the term melonic graphs in one of their papers, I think dates back to 2011. But there are even earlier papers which called them blobs or something like this. You'll see in a second what precisely. So as I mentioned, if you think about this vertex with blue lines crossing under each other, you can view it as just a tetrahedron. So, so the 3-geometry interpretation emerges from the dual graphs, just like what we had for the matrix model. But this, upon closer inspection, like when they solved the large N limit, they realized that this doesn't work so well because the universality class you get are just branch polymers. They basically didn't get something nice like the surface theory for quantum gravity. So here you can think of these, for example, each of the vacuum graphs as some kind of tetrahedra glued along faces with faces identified. Okay, so the melonic limit, the claim is that only a very special subclass of graphs survives. They're essentially obtained by iterating. In each propagator, you insert this blob, and you keep iterating. And then you get this ladder-like structures where more and more rungs of the ladder appears. And this ladder-like structure, in some sense, is why you get these rather uninteresting dual 3 geometries. But now we think, as I'll discuss, the application is not so much to this 3-dimensional quantum gravity, where it doesn't appear to give a very interesting story, but just as a new type of solvable large N limit. And the connection with the Sachdevia-Kitaev model, which I'll describe in a second. So why call them melons? That's a commonly asked question. I think this term was coined in this paper. Probably watermelon comes to mind more because watermelon has rather well-defined stripes. And in theory, with phi to the q interactions, you sort of see the stripes of the watermelon. But there were earlier mentions of the same type of subclass of graphs in phi-4 theory. Now, non-melonic graphs, they're all suppressed. So here is the first non-melonic graph that you can draw with 3 vertices. You can sketch the maximal number of loops, and you see that this one actually is suppressed by n to the 3 halves. So it turns out it's easy to see that none of the graphs with an odd number of vertices is going to be melonic for some obvious reasons. So here is a list of vacuum graphs from a book by Kleinert and Schulte-Frohlinde. And you see that a very small number of them are melonic. For example, this one is a melonic graph, this one is not. Then only this one is out of the quartic graphs, and of 6th order, there are only 2, and the rest are all non-melonic. So out of the first 27 graphs without tadpoles or snails, only 4 are melonic. So it's an even smaller class than planar graphs. And as shown in this paper, the number of melonic graphs with p vertices grows as c to the p. So it gives you a controllable convergent expansion. Now, how do you prove the large N scaling? It actually utilizes 't Hooft's idea of that the topology, the power of N is the Euler characteristic, but here you have to use it in the following way. You can start, so when you draw this triple color graph, you first erase all the lines of one color, and that gives you 3 possibilities of just 2 color graphs. And for the 2 color graphs, we know how to count the power of N, or how to count the number of index loops. This is just through the Euler characteristic. And our goal is to count the sum of the number of red, green, and blue loops. So if you counted the number of, say, red plus green loops in terms of the Euler characteristic of this graph, you can repeat it and then just add them all up. You add up the Euler characteristic of the blue-green, blue-red, and red-green graph, and this leads you to the formula for the total number of index loops, which is just 3 times the number of vertices over 2 plus 3 minus the genus of each of these, sum of the genus of each of these subgraphs. And then you see that since genus is obviously non-negative, the highest power of N is when genus is 0 for each of these subgraphs. And that immediately gives you this Gn to the 3 halves. So it's a very simple, like it's a 2-line argument that tells you that nothing can beat this power, Gn to the 3 halves to the number of vertices. It's actually not, as there is still some more steps you need to make to show that only melons dominate, but this gives you a flavor for why this large N limit exists. So it's a very simple story. And now I just want to, something that's much more recent is what about the series of tensors where the indices are indistinguishable. For example, symmetric traceless tensor of a single group On. This is roughly what people started with, but they couldn't analyze it. But then with Tarnopolsky, who is my former student, we started just looking brute force at graphs with the tracelessness condition. And it looks like there is still melonic dominance for these graphs. We basically checked up to 8th order, which I'll show. There are 177 graphs without snails or tadpoles. And we could see that only melons dominate. And then we were told by private communication by Shapasnik Masola that it works even to higher orders. And then recently there is a proof that nothing beats the melons, but it still doesn't prove that only melons dominate. So you're led to drawing lots of pictures like that, like these, and these numbers are just the scaling in the theory of distinguished index tensors and symmetric traceless tensors. And again, you see that only melons dominate. These are melonic graphs. So it still remains to be fully proven, but it looks like this melonic limit is, is quite general. In these theories, when you have a symmetric traceless tensor, the propagator is much more complicated. You first have to symmetrize and also subtract the trace pieces. Or you can have a theory of, for example, anti-symmetric representation of N, then there are only 6 terms. And the computer can do this index algebra, but rather slowly. So it takes a long time to compute all the diagrams. But the fact that it seems to hold to high order is almost a done deal that it still works, which is quite interesting. So now the connection with the SYK model, that's something that probably all of you heard a lot about. It's a model with random interactions, where J is this Gaussian, has a Gaussian distribution. And you can take, for simplicity, Q equal 4, so 4 of the Majorana fermions interact at a time. So a lot is known about this model, and in particular, so NSYK is the number of these Majorana fermions. I added the subscript SYK to distinguish from the N that I had in this ON cube theory. In fact, we'll see that NSYK is of order N cube, because, but then essentially people realized, I think I took this picture from one of the papers that are not mine, maybe Maldacena Stanford paper. So when you do this order averaging, which is the dashed line, you again see that only melons dominate. Solid lines are fermion propagators, and dashed lines mean disorder average. So you see some connection with this theory of tensors, and the connection appears to be quite precise in the leading large N limit. And for example, here is the paper which made this connection, an SYK-like model without disorder by Witten, which appeared the evening of Halloween in 2016. So it makes it tempting to, pumpkin is another striped vegetable. It's very generically striped, so. Yeah, well, no one is convinced by this title, melonic, because melons don't always have stripes, so there is still some freedom of renaming this theory. So the model that Witten wrote down, it had some elements of the interaction that Gourau wrote down, and actually in his 2009 paper, is you take four anti-commuting fermionic fields, psi ABC, 4 copies of this, and each one is a Majorana fermion, just like in the SYK model. And then you write this type of quartic interaction, which preserves 6 ON symmetry. So it has ON to the 6 symmetry. Each tensor is in a different trifundamental under this, this symmetry. So when you think about it as a tetrahedron, you see that each edge of the tetrahedron has a different color. For example, psi1 ADE has 3 different colors coming in, and these edges of the tetrahedron correspond to ON groups. So there are 6 types of ON groups, and that corresponds to 6 colors. And the gauging of the symmetry just removes the non-singlet states and operators. So if you gauge, you have to just restrict to only the singlet sector of the theory. But this theory is still rather can be simplified further, which is what was noted by Tarnopolsky and me. It turns out that that Gourau-Witten model is, sorry, it's SYK-like, but it's not literally like the SYK model. It appears to be the tensor counterpart of the 4-flavor Gauss-Rosenhaus generalization of SYK, where you take these chi's with 4 different flavor labels. And this is suggested by studies of combinatorics and also of the operator spectra, that you basically see that there are more operators in this theory than in the basic SYK model. So which model is the closest to the basic SYK model? And we believe that it's the model with just 1 tensor and 3 gauge group. In other words, it's like the model I had written down before, except you take psi to be a Majorana fermion. And you put in a tetrahedron interaction. So there is ON cross ON cross ON symmetry. And I drew these ONs with different colors to distinguish them. So that's the model. And that's part of the reason why I came here, because it does have the definite qubit connection. These psi's are just the gamma matrices of the Clifford algebra of O and cube. And when you start looking at the states, you basically have qubits. Like you can represent them as qubits. There is 2 to the n cube over 2 qubits. And this is just a particular Hamiltonian acting on this set of qubits. And the Hamiltonian is completely not random. It's just a nice symmetric Hamiltonian. So again, the connection, you can think of psi's as these vertices of the tetrahedron. And now the tetrahedron has 2 red edges, 2 green, and 2 blue. So it's a bit simpler model than Gouraud-Witten and easier to draw like. So this is basically, I already drew this. This is the propagator. This is the vertex. You start combining them together and so on. So I probably won't have time to show this in detail, but the structure of a lot of large N calculations is identical to what you see in the SYK model because of the Mellon dominance. Except, as I mentioned, N of SYK model has to be taken to be N cube, right? Because there is N cube species of these Majorana fermions. Each of these indices runs from 1 to N, and the indices are distinguishable. Now, but there is somehow much more to this model, though, because you can, in addition to these operators with derivatives, which have been studied extensively in the SYK model, there are various multi-particle operators where you take some large number of fields and contract them together. And we tried to count them with Bulichova, Milokhin, Tarnopolsky. That's my most recent paper. We tried to draw these colorful pictures, for example, of 8th-order operators. It turns out some of them are related by equations of motion to these operators with derivatives, but others are not. And the number of such operators grows very rapidly, like a factorial. So it's a vast growth of operators, and we still have to understand what it all means. In terms of the Schwinger-Dyson equations for the propagator, you can literally transcribe what was done in the SYK model, the large N solution, and you find exactly the same result. You don't need this order, you just need this Mellonic large N limit. And then similar with the Kitaev's ladder summation. You can sum ladders using the kernel, and you find exactly the same spectrum of two-body operators. So this is the spectrum of two-body operators, which I already mentioned. That again has this famous H equal 2 mode, which is dual to dilaton gravity and has exactly the same higher modes. But as I mentioned, there is vastly more other operators which still have not been solved in a similar level of detail. Now, a model with a complex fermion, Daniel asked me this question. It's another very natural model. You take complex fermion and just contract indices like psi, psi bar, psi, psi bar. Actually, you kind of have to normal order it, but it doesn't matter too much. And then the symmetry is SUN cross ON. The middle index has to be ON because the middle index has to contract 2 psis, but the first and third index contract psi and psi bar, so they can be SUN. So you get this symmetry. This is the analog of the complex SYK model with Dirac fermions rather than Majorana. Now you have 2 classes of operators. You can have N being both even and odd. So the lowest operator is the U1 charge, psi bar ABC, psi ABC. So you have these additional solutions that are present in this model. The first solution is H equals 0 corresponding to the U1 charge. So here there are these orange lines which are exactly the same as in the basic SYK, and then there are the black lines which correspond to the additional sector present in the complex model. Now, can you play this game for theories in higher dimensions? I was very excited about this, and we tried various things. It's definitely harder. For example, if you do the most obvious thing, just write down 5-4 theory in 4 minus epsilon dimensions or in 4 dimensions, you get some problems. The first problem is that this type of interaction does not give you a positive definite potential. The potential tends to be unbounded from below, but even in the large N limit, there is the following problem. As an amusing historical note, Potoshinsky and Pokrovsky actually had the Schwinger-Dyson equation for this model in 4 dimensions. Somehow they just wrote it down. They certainly didn't know that it comes from tensor model, but that was essentially resumming melons for the green function. So you get the scaling solution, but now if you look at the spectrum of 2 particle operators, you run into a problem. And the problem is the following, that you get a complex mode. Like formally, you get a complex solution for the operator phi ABC. It has to do with the fact that you don't truly have an honest CFT. For example, if you do it in 4 minus epsilon dimension, and this is explained in detail in my paper with Jomby and Tarnopolsky, you have to include, because it's a renormalizable theory, you have to include the other all possible ON cube invariant terms. And their values at the fixed point are actually complex. So you have to include the double trace and so-called pillow. So there are several operators, and while this one is real, the others turn out to be complex. And you see this in the complex value of the 4 minus epsilon expansion. If you go down to lower dimensions, you do see complex dimension. Roughly speaking, it's like having an unstable CFT, which in ADS space, there is a scalar field violating the BF bound. That seems to be the picture. So in some formal sense, you can study it, but it doesn't honestly exist. Actually, at large N, you often find out into these CFTs that are sort of formally there, but maybe not there in a physical sense. Okay, so let me finish. So let me just do a brief review of the space of SYK models and their tensor counterparts. So the basic SYK model for some number of Majorana fermions coupled with this random interaction, the closest counterpart seems to be this ON cubed tensor model that Tarnopolsky and I wrote down. It has exactly the same partition function in the large N limit, but the operator spectra seems to be much richer. And there could be very big differences when it comes to 1 over N expansion. When you look at the leading 1 over N correction in this model, it's only 1 over N. Well, here, this would correspond to 1 over N SYK to the 1/3 power, which certainly is not present here. So the 1 over N corrections are very different. And remains to be seen if you can study them as explicitly. Then the Gourau-Witten model, it's a 4-flavor model with ON to the 6 symmetry. This seems to correspond to the Gross-Rosenhaus version of SYK model with 4 flavors also. Then the complex SYK model with Dirac fermions, and this corresponds to this model with essentially UN cross ON symmetry. So let me conclude. There seems to be a new window on large N theories, which while less generic, nevertheless seems exactly solvable and rather nicely solvable, at least when it comes to models in 0 and 0+1 dimensions. Like, the 't Hooft large N limit was essentially introduced for QCD, but then was applied to just one matrix model and matrix quantum mechanics. Here, so far, there is no analog of tensor version of QCD-like theory, as far as I know, but there are definitely these 0 and 0+1 dimensional models, and in particular, the model of a large number of Majorana fermions with ON symmetries looks rather interesting and very hard to solve, incidentally. it's very hard to solve its spectrum because the number of states grows so rapidly. It's 2 to the n cube over 2. So the vector and matrix models certainly have come in very handy, and in particular, we hear a lot about the 't large n limit in the context of ADS-CFT, and starting to understand the 1 over n squared corrections. But the tensor or melonic or pumpkin large n limits seem relatively new, and we don't yet know what is the range of possibilities here. But definitely, it seems like there are some SYK-like models without disorder. So maybe, one interesting thing is that you can just impose the constraint that you're only looking at ON cube invariant states. And this is a some subset of states which you can figure out. And this subset of states has to exhibit all the characteristics of the SYK spectrum distribution of states when you crank up n. So perhaps this will teach us, maybe give us another angle on near ADS dual geometries and black holes. So it looks like a little bit in spirit like this matrix quantum mechanics of Hermitian matrices, but more complicated and more modern and more qubitsy. So I'll end with that.
Okay, any questions?
So my understanding with these extra states that you have, let's say in the SYK-like fermion model, was that they tend to dominate the thermodynamics, that you have a very high number of low energy states that give you a Hagedorn temperature that tends to 0 in the large n limit.
Do you mean states like eigenstates of the Hamiltonian?
Right.
No, I don't think we will get, I think the distribution of those states should be very similar to SYK. And I believe that the free energy of the model at very low temperature should be the same as SYK. What is different is that you can write down many more invariant operators. That is true. Like, yeah, there is a sort of the operator point of view and the state point of view. What I was saying here is that there are these many operators which definitely make sense in the tensor model, things like these. It turns out that the sum of these 3 operators is literally like psi d cubed psi. If you apply equations of motion, you get these operators. But then there are these additional ones, and their number explodes as you go to higher n. So you can, for example, ask what is the spectrum of scaling dimensions of these operators. And we partially had some comments on this in our last paper, but yeah, I think the difference is largely, for various quantities, is largely in the 1 over n corrections compared to the SYK.
I'm recalling this intuition that they're roughly order n squared light degrees of freedom in addition to the h equals 2 mode.
Right. I think they affect the 1 over n correction. Right. But yeah, they have to do with the gauge. Roughly speaking, they may have to do with gauge fields in the bulk. Because there is this exact ON, like in the SYK model, only in the replicated sense there is ON symmetry. Here there is just the basic ON cubed symmetry. So there are gauge fields associated with that. And they're kind of another set of light modes.
So in terms of trying to prove the dominance of the melons, I mean, the obvious thing to try to do that is to try to introduce some auxiliary fields and then integrate out the tensors and see if you can somehow, pull out a factor of n.
Well, the auxiliary fields will have at least will have 4 indices. Yeah, it's different from the vector. In the vector model, the way you solve the model is you introduce this Hubbard-Stratonovich auxiliary fields, which has no indices. Here, if you look at this Hamiltonian, right, you have to introduce something with B1, C1, B2, C2 indices.
Yeah, but I mean, and so in SYK you can do this though, right? There's this there's these bilocal
Right,
fields,
right,
so
right.
it doesn't seem crazy that there would be some.
Yeah, it's definitely worthwhile. I think it's proven that the melons dominate. That's already proved.
Oh, I thought you said that in some of these models it's proven that nothing beats the melons.
No, in this model it's
Oh, sorry,
proven.
in
In
this
this
one it's
model
proven,
it's
okay.
just proven.
Yeah, I see.
This more complicated model where you take just one ON group and symmetric traceless tensor,
Oh, okay.
it's almost proven already. Like there was a recent paper by Gorao and Carrozza.
Yeah, but I guess if they're master fields, then it's obvious.
Right. Somehow the way the proof has worked in these models is different. It's very combinatorial. It's hard. It's a very mathematical field. In fact, many people who work in this field are in the department of combinatorics of some French university. So it's interesting to they're not necessarily field theory people, but they understand very well how to count graphs. And so it's these techniques of counting graphs that prove things here. But maybe there is something better indeed, like applying some more field theory tricks.
Okay, let's thank Igor again.
Okay.